This video is a tutorial on LASPATED Matlab calibration functions. These functions will be illustrated on examples based on simulated data. For the first example that I am going to use, points arrive in a two-dimensional space over time according to a non-homogeneous Poisson process. There is only one type of point, and the region under consideration is the square 0,10 square shown in this figure. This square is discretized into a 10 by 10, that is to say 100 square zones, and each zone belongs to one of two types, blue or red, as shown in the figure. Let me now give you the rate function lambda of the Poisson processes for this experiment. So lambda is a function of space and time. So lambda of st, where s is the space variable and t the time variable, this is 0.1 for every s in the blue region, or the time intervals that end at odd time intervals, so 1, 3, and so on. And lambda of st is 0.5 in the blue region, or even time intervals that end 4 times 2, 4, 6, and so on. And similarly, lambda of st is 0.5 when s is in the red region, and when t belongs to an odd time interval that ends at time 1, 3, 5, and so on. And lambda of st is 0.1 or s in the red region when t belongs to an even time interval, a time interval that ends at times 2, 4, 6, and so on. On this figure, in this slide, I have represented the intensities in red and blue zones for odd and even index time intervals. So indeed, we see that we have piecewise constant intensities. Now, let me show you how to use MATLAB LASPATED calibration function to calibrate the intensities lambda when we have a sample of the Poisson process given by this rate function. So I will open the MATLAB command window, and I will first show you the signature of the calibration function. The MATLAB calibration function has the following signature. It is called LASPATED, and it has the following input variables: model, that will allow us to know if the model is with covariates or not, and the observations will give the number of observations or every combinations of CIT, and the arrivals. This is the number of arrivals for every combinations of CIT. Then T, this is the number of time windows, the time partition, or this is the number of subregions in the space partition. C is the number of arrival types. Durations is an array that gives the durations of the elementary time windows. groups is a cell array that will provide the elementary time windows for each group. Each group of T provides the group to which time window T belongs to. Then we have some parameters that are related to the optimization process that we will see later. Then we have a structure param that we will see later. And the outputs are lambda, the vector of intensities. We have 3 dimensions, CIT, and obj will give the approximate optimal values of the loss function along iterations of the optimization process. So what we are going to do is, for the toy problem that I have just presented, we are going to build the input variable for LASPATED compute the intensity. So let us start providing the model. So model, the first variable is a string which needs to be no reg of the model without coverage. Start with the model without coverage. Model is the string no reg. Calibrate the model without coverage. So the second input variable, as I was saying, is NB observations. And this is a 3-dimensional array with NB observations of CRT, number of observations for arrival type C, region R, time window T. So to initialize this variable, let us initialize first C, which will be the number of arrival types. For this problem, for this toy problem, we have 1 arrival type. Let us initialize the number of subregions of the space discretization. So as I was saying, we have discretized our square to 100 squares of unit area. So R, the number of regions, is 100. So actually, the theoretical lambdas are periodic with period 2. But we assume that this is not known to the modeler. So actually, if the duration of the period is 6 hours, then this period 2 means half a day, 12 hours. And we will assume that the period defined by the modeler is 28. So 28, actually, this would be for elementary time windows of 6 hours. This would be a period of 1 week. So the modeler will assume that the period is 1 week. So capital T for us, number of elementary time windows will be 28. Modeler assumes we have a period of 1 week, but actually it is of half a day. So let us assume that we have 20 observations as an example, or every combinations of CRT, of the arrival type, subregion, elementary time window. So I will call be observation total 20, the number of observations that we have for every combination of CRT. And in this case, and the observation is an array with 3 dimensions. It will be 20 for every combination of CRT. I will have 20 observations. So as I was saying, say that the duration of an elementary time window is 6 hours, 6 time units, let's say hours, 6 hours. And then we define the groups. So actually the theoretical period is 2 elementary time windows of 6 hours. But let us assume that the modeler does not know this information, but he will still use time groups, but instead of 2 time groups, he would use 4 time groups. So in the first time group, he will use time intervals with indexes 1, 1 plus 4, 5, 5 plus 4, 9, so 1, 5, 9. Then in the second time group, he will put 2, then 2 plus 4, 2 plus 4 plus 4. So we will have in the second time group 2, 6, 10. In the third time group, we'll have 3, 3 plus 4, and so on. And in the fourth group, 4, 4 plus 4, and so on. So I will build the variable groups in this manner in MATLAB. As I was saying, groups is a cell array, and you will see, as I was mentioning, that in the first group, I have the elementary time windows with index 1, 5, 9, 13, and so on until 25. We call that capital T is 28. Then in the second group, we start at 2. And then plus 4, 6, plus 4, 10, and so on. In the third group, we start at 3, plus 4, 7, plus 4, 11, and so on. And finally, we have 4 time groups. In the last one, we have time window with index 4, then plus 4, 8, plus 4, 12, and so on. So these are the time groups. Once we have defined this time group, we can define the variable which group I have mentioned when I gave the signature of LASPATED function. And you see which group is. So which group 1 will give the index of the group for time window 1. It is 1. Which group of 2 will give the index of the group of time window 2. This is 2. Which group of 3 is 3, which group of 4 is 4, and so on. So which group is periodic with period 4? Which group is a vector of size 28 with the entries being 1, 2, 3, 4, 1, 2, 3, 4, and so on. Entries periodic with period 4. Now we need to define the intensities lambda. So if we recall, we have the intensities that are defined in the red region and in the blue region. So I will first define the intensities for the elementary time windows of the first group. So here it is. I call theoretical lambda R for red. The true values of lambda in the red region. And here I define them for the elementary time windows of the first group. And it takes the values 0.5. And we do the same for the elementary time windows of all the other groups. Let us do that for group 2, 3, and 4. And we do the same for the blue region. So we define the theoretical lambdas, true lambdas, in the blue region similarly. Now, if we remember, for space regularization, we have some penalizing weights, Wij. So what we will do, we will say that Wij is some weight W, when I and J are neighbors of the same type. So the same color, say. So I will define here and X and Y, the horizontal and vertical discretization step. We discretize in a 10 by 10 rectangle. And if I go back to the figure showing the region of interest, so we will number the regions. So for the first line from left to right, the number of the regions will be 1 to 10. So 1, 2, 3, 4, 5 for the first red bottom regions, and then 6, 7, 8, 9, 10 for the next blue regions. And on the second line, the red regions, the red subregions, will have numbers from 11 to 15. On the second line, the blue regions from 16 to 20, and so on. And we attribute the type to subregion. So we have 100 subregion in this space discretization. And the type will be 1 for the red subregion and 2 for the blue subregion. Let us attribute the types to the region. I will share again the MATLAB command window. So here we attribute the types to the different subregions. And now we need to build the input variable NB arrivals that will give the number of arrivals for every combinations of CIT. So first, we will define a vector, RMAP, that will give the successive numbers of the red regions. So as I was saying, the first 5 bottom regions are numbered from 1 to 5. Then the next 5 red regions on the second line are numbered from 11 to 15. Then 21 to 25. And 31 to 35, 41 to 45. And then 56 to 60, 66 to 70, and so on. Here, starting here from 66 to 50, we start to look at the subregions, the red subregions of the upper right corner. And similarly, we provide the indexes of the blue regions. B-mapping is a vector providing the indexes of all the successive blue regions. So we will have a vector sample. So this will contain the sample of observations. So for observation J, the number of arrivals for time window T, region R, and arrival type C will be stored in this cell array, actually. In this entry of the array. So I will show you the code for the generation of the sample. So we will have a vector NB arrivals. This vector NB arrivals, that is one of the input variables of LASPATED, I have mentioned before. So NB arrivals of CRT will be the number of arrivals for arrival type C, subregion R, time window T. So I recall this is the number of observations that we have. And here is the code for the generation of the sample of observations. Let us take a look. For every elementary time window T from 1 to 28, for every arrival type, what we do, we first generate the sample from the Poisson distribution from the intensity of the red region for this value of TP. So the theoretical intensity times the duration of the elementary time step. And for this TP, the number of observations that we have is NB observations total, which is 20 in our example. So now we have actually a vector here that has size 20. And in this vector, every entry is a realization of a Poisson distribution with this intensity. So for every entry here, for every observation, from 1 to the total number of observation, which is 20, we have a certain amount of arrivals that was observed here in the red zone, and we need to discretize the process to distribute these observations in the red squares corresponding to the discretization of the red zone into 50 small squares of unit area. So what we do is that we will take assuming that we have say 10 observations in this red zone, we take a sample of time of size 10 of the uniform distribution over the integers from 1 to 50. We have actually 50 red squares of the discretization of the red zones into red squares. And this sample from the uniform distribution will correspond to indexes of the red squares that will be chosen for building the sample observations in the red zone. And that's where we will use the R map vector. So for instance, here, if we had just 2 observations in the red zone, and for the sample from the uniform distribution over the integers 1, 2 until 50, if we had chosen, say, 3 and 10, then we would have an observation into red square 3 and red square 10. Red square 3 will be the subregion with index 3. And for the 10th red subregion, we obtain the square of the red discretization with index 50. And we do the same in the blue region to build the sample of observations of arrivals in the 50 blue squares of the blue discretization. So now we have built the vector NB arrivals. So we have the number of arrivals for every combinations of time, subregion, and arrival type. And we are going to define now the neighbors. And we'll use the natural definition of neighbors. If I go back to the figure, then the square here, the red square in the bottom left corner, will have 3 neighbors. So one neighbor above, immediately above, one neighbor at the right, and one neighbor in the diagonal. If I take a red square or a blue circle inside the square, then they will have 8 neighbors. 3 below, 3 above, 1 at the right, 1 at the left. So let us define these neighbors. Let us go back to the MATLAB command window. I have here fields cell array where neighbors of 1i will be the list of neighbors, will be the list of the indexes of the neighbors of subregion I. So for instance, here are the neighbors for region index 1, region index 2, region index, say, 6, and so on. So here we see that we have 8 neighbors in the center. So you can check the code here. We go through all the subregions. For every subregion, we compute the coordinates of the centroid of the center, xi, yi. Then, depending on these coordinates, we will have neighbors on the left or not, on the right or not, above or not, below or not. And we easily define the neighbors. And for the distance is not used. Here we assume dij is 1, so we will just have, for the calibration, the weights wij for space penalization. So let us continue. We need to define parameters for the optimization method. So you can check on the paper. Sigma is a parameter for the optimization method. We can take 0.5. Per max is the maximal number of iterations for the optimization algorithm. Let us take 30. Epsilon, let us take 10 to the minus 3. This is the epsilon that we have used to reformulate the problem equivalently as a differentiable convex optimization problem, differentiable over the new feasible set defined in terms of epsilon. So lambda 0 is the initial point. So let us take epsilon, vector of epsilon, and the dimensions are CRT. So let us define a weight 1. And the weights wij will be 1, actually, if I, aj are neighbors of the same type. So if they are red or blue neighbors. And then, as I was saying, there is a last input variable, which is a struct param, which has several fields. The first field, neighbors, is the cell array neighbors. We have just defined what are the neighbors. Then we have a second field, which is type, which gives the type of every region. So we will have a space panelization for neighbors of the same type, so the same color here. Then if you recall, in the space penalization, we have the dij, but here we do not use them, so we take them equal to 1, which amounts to discarding them. So params.distance is the vector distance. Actually, it's the matrix distance, where distance of ij is the distance between I and j. Actually, the weight I defined before is not for space, but for time penalization. So for the struct param, the field weight is actually a vector providing for in entry I, the weight Wi, Wj corresponding to the group J of index I. So here we assume that all the weights are equal to 1. This is the time groups. And in this example, so params.alpha, this is used for space regularization. And the Wij will be this param.alpha when I, Aj are neighbors of the same type, neighbors of the same color. And now we have defined all the input variables needed by LASPATED to compute the intensities lambda. So we call LASPATED with those input variables that we have defined. So it says that the model without regressors is chosen. And as I was saying, the outputs are lambda, the matrix of the lambda CRT, and obj will be a vector of the approximate loss function value along iterations. So lambda, this is the matrix with all the values, the lambda that were approximated. We can see that the size of lambda. So here, this so lambda is lambda of CRT. So C has dimension 1. The number of subregions is 100, and the number of elementary time windows is 28. This is indeed these are indeed the dimensions of lambda. And we can take a look at the evolution of the loss function value along iterations. To show you this. And we can see a stabilization of the values. The optimization algorithm has converged. So let us go back to Matlab window. And now I will show you how to run cross-validation to calibrate the weights. So we need to provide a list of candidate weights. So let us say that we want to take as the weights for time penalization, for the time group penalization. These weights here start at 0, 10 to the minus 2, 0.05, 0.1, 1, 5, 10. We have a set of values here, goes until 400. And same for space regularization. We have a set of weights that we call alphas. They correspond to the previous params.alpha. So what we have is is a function, cross-validation function for the calibration of the weights. So among those candidate weights, we'll select best weights using cross-validation. So for that, we need to define the proportion of observations used for training the cross-validation, let us say 20%. And then the function, the LASPATED function to run cross-validation is as follows. Let me show you the signature of the function. I have stopped the process here to show you. So the function is cross-validation. Most of the parameters are the same as the LASPATED function that we ran before. So model, sample, this is the sample of observations that we built. T, RC, that have the same meaning as before, sigma, lambda 0, iter max, proportion. We have seen that before, epsilon, duration, groups, each group, weights, and param. So we see that actually, compared to LASPATED, the only different input parameter is sample, but we have defined sample already before. This is the sample of observations. And what cross-validation LASPATED function will return is CPU time, the time needed to compute the best weights. And then weights will give you the best weight for the penalization of time groups, and actually of space group, because to simplify in this cross-validation function, we assume that the same weight, when we test the weights, we assume that we use the same weight for time and space regularization. And then lambda will give the corresponding best lambda. So if I run this function, then you will see on the command window the different values of the different index values corresponding to the different values of the weights tested. And after a while, takes some time depending on the size of data, you will get the best weight, the CPU time needed for the computation, and the best lambda. So here again, I will stop computation, but this is how you would run cross-validation. I am now going to show you how to use MATLAB function LASPATED to calibrate the parameters of the model with covariates. We will use a toy problem with simulated data. The region under consideration is S010 squared. For each point S in S, we have 3 attributes. So the regressor X of S at location S has 3 entries, X1, X2, and X3 of S. For instance, as covariates, it would use the population and 2 land types. So X1 of S could be the population at location S. X2 of S could be 1 if the land at location S is used for commerce and 0 otherwise, and X3 of S1 if the land at location S is used for manufacturing and 0 otherwise. So the 2 land types here would be commerce and manufacturing. We also consider 2 settings, one without the holiday effect and one with the holiday effect. And in both settings, the rate function lambda is periodic with period. We have explicit analytic values for the rate function. So in the setting without the holiday effect, lambda is defined on the Cartesian product of S and the time interval 0 capital T. And lambda of ST, when T belongs to a time interval that ends at an odd time, so for T in 0, 1, T in 2, 3, etc., the rate function lambda of ST is a linear function of X S, and it is beta 0 transpose X of S. Beta 0 is known explicitly. This is a 3-dimensional vector with entries 0, 3, 6, and 3. And lambda of st, when t belongs to an interval that ends at an even time, so for t in 1, 2, t in 3, 4, and so on, lambda of st is beta of 1 transpose x of s, and beta of 1 is a 3-dimensional vector with values 0.05, 18, and 6. In the setting with holiday effect, the rate function lambda has an additional parameter h, indicating if we are on holiday or not. So lambda of hst, when t falls in holiday, h is equal to 1, and lambda of hst is when t belongs to a time interval that ends at an odd time step, it is beta of h0 transpose x of s. Is beta of h0 known explicitly. And when t ends, when t belongs to a time interval that ends at an even time, then lambda of hst is beta of h1 transpose x of s with beta of h1 known explicitly, with h equal to 1 when t is on a holiday and h equals 0 otherwise. As in the previous model, as in the previous example that we used to test the model without covariates, we partition S into two subsets, the blue region and the red region as before. So the red region is actually made of two squares, one in the bottom left corner and one in the upper right corner. And the blue zone is made of two squares, one in the upper left corner and one in the bottom right corner. As before, S is discretized for estimation purposes in 100 square zones of unit area. And we consider for x1 of S a function that is known explicitly, and that is given here on this slide, and that depends on 40 realizations of independent random variables uniformly distributed on 0, 1. So here is the x1 function, and I am showing you here graph of this regressor function x1 on S. And we also have known values for x2 when S belongs to the blue region. Then x2 is 0.25, x3 is 0.5. And when S belongs to the red region, x2 is 0.5 and x3 is 0.25. So now let me show you for this model with covariates and for this example, how to calibrate the beta. So I will show you the MATLAB command window. As before, we are going to define the number of horizontal and vertical discretization steps. This is 10. The number of subregions, as we said, is 100. C, capital C, is the number of arrival types. We have one arrival type. Even if the model is periodic with period 2, we will assume that the model we'll use actually a model with period 4, so it does not have the information available. Capital D will be 15. We consider a setting with holidays here. So we have estimators lambda CGRT, or every arrival type C, actually you want arrival type. D takes 15 values, 7 for the 7 days of the week, and we consider 8 holidays. So the cardinality of the number of days plus holidays is 15. So this is capital D. Number of weekdays, 7 plus holidays, 8, 15. We'll consider for the test that we have 20 weeks of observations. So this is the corresponding number of years, assuming that we have, say, for this for simplification, years of 52 weeks. We take the duration of an elementary time window of 1 time unit. We have a variable, NB holidays year, which is the number of holidays during the year. Then we will define the cell array is holidays. So is holidays of J dot B will be a Boolean, which is 1 if we are on a holiday and 0 otherwise. And if we are on holidays, the field is holidays of J dot K, or date J, will give us the index of the holiday. So is holidays is field. This way, we first initialize it. We will assume that the 8 holidays are the first 8 days of the year, just for simulation purpose. So the corresponding indexes are 1, 2, 3, 4, 5, 6, 7, 8. And then we fill this cell array is holidays. This allows us to know for a given observation, this observation is on a day which is holiday or not. Then, as I was saying, we have 3 covariates. Assume that we have a first covariate, so x1 of s, and we can think of the other 2 covariates as lamp types. So we have in this situation 2 lamp types. So what is the size of the betas? So to store the beta, we need an array with dimension C, D, T, and Belen types plus 1. Since the beta are indexed by CDT, the arrival type, the day or holiday, and the time index, and every beta CDT has dimension and Belen types plus 1, which is 3 in our case. Next, we need to discretize the model. So we need to define regressors for every subregion R. So we'll define values of regressors. We will have actually 3 times number of regions, that is to say 300 values of regressors, which are the population and the 2 lamp types, for all the 100 subregions. The betas are given on the slide that I have shown you. So I will simply fill the betas as I have shown you. We'll use a variable counter initialized to 1. Let us fill the beta CDT when D is not on holiday, so for the weekdays that are not holidays. So these are the betas corresponding to weekdays that are not holidays for D from 1 to 7. And the betas that I have filled here are those that I have shown you on the slide. Then we fill the beta for days which are holidays. So now we fill the beta CDT J for every CDT J. Here, G going from 8 to 15 for the holidays. Next, we need to build the values of the regressors for every subregion. So for regressors 2 and 3, we have constant values. And for regressor 1, you can see in the LASPATED paper available on arXiv how to get an explicit expression of the discretized value of the regressor in every subregion. So this is the code that allows us to build the regressors for all the subregions. You can see that those loop here, we fill regressors of J counter here, where counter goes through all the subregions. And the first variable J is 1, 2, 3, the 3 types of covariates that we have. For the first entry, we call a function compute x1 that I will show you. That computes the discretized values of the regressors in the subregion as shown in the LASPATED paper. And for the second and third regressor, we have constant values. So I am going to show you the code to compute x1 in all the subregions. Here it is. You can find this code and actually the MATLAB code that I am showing you in this tutorial on the GitHub page of LASPATED project. So here, what we do in this function compute x1, we compute for a subregion that is given by the Cartesian product of I-1i, j-1j, and that is of a given type, which is when the type is 1, we are in the red region, and when the type is 2, we are in the blue region. So this function computes the integral of x1 over the region Cartesian product of I minus 1i, j minus 1j, and y, the output is this integral. Now that we have built the discretized values of the regressors, we are going to build the values of the sample of observations in all the subregions. So we'll call sample the cell array that will contain the samples of observations. So sample of CDTI will be the sample of observations for arrival type C, day or holiday D, elementary time window T, and subregion I. We'll have an array that will count the number of observations for every combinations of CDTR. We'll have an array NB arrivals that will count the number of arrivals for every combination CDTR. We have a vector index beta that is used for Bureau B to know the indexes of the different beta variables. So beta CDTJ in vector beta as index beta of CDTJ. Then we define the size of the decision variable for our optimization problem. What we want to calibrate in the model with covariates are the beta. Beta are indexed by CDT, and every beta CDT has the dimension NB type plus 1, that is to say 3. So this is the dimension of the optimization problem that we will have to solve. Then we build the samples of observations. So here is the code for building the samples of observations. We loop through all the indexes for which we have observations, which is a number of weeks times 7. We check if the corresponding day is a weekday that is not holiday, or if it is a holiday. And then we compute for every elementary time window and for every subregion the corresponding rate of the Poisson processes for that day or holiday using the model with covariates. That is to say, the rate is beta transpose the vector of regressor for that region I where we are. So once we have the rates, we build for a given region, we build our samples. So we generate a realization from the Poisson distribution with the corresponding rate for that elementary time window, that subregion, the day we are at. And we update the variable sample, NB observations, and NB arrivals correspondingly. Then we need to define epsilon that appears in the model with covariates in the reformulation of the problem as an optimization problem that is differentiable over the feasible set. Let us take epsilon 10 to the -6. We need to initialize beta, the vector of parameters. So let us initialize it with the values 2 epsilon. It has size x. Sigma is a parameter of the optimization method, say 5. Max is the maximal number of iterations for the optimization method, which is projected gradient with line search. For the model with covariates, we do not have time groups. So we define empty arrays for groups and which group. But LASPATED could be extended to incorporate groups in the model, time groups, in the model with covariates. So we have kept the variables groups and which group that could be used in a future version of LASPATED. Then we have the structure param, as before. Is specialized to the model with covariates. For the model with covariate, we need to inform index beta. We need to inform the number of days plus holidays, which is 15. We need to inform in the field regressor the matrix of regressors. We inform the number of regressors, which is 3 for us, 1 plus the number of non-types. We give the size of beta in the field size x, number of observations in the field NBOps, and we have a vector of lower bounds, which is 0 in our situation. And the variable model is the string reg for regressor. And as before, we call LASPATED function for the calibration of the model. Now it indicates that the model with regressors was chosen. And as before, it has 2 outputs, lambda and obj. Actually, lambda here is the vector of beta, and the rates are beta transpose, beta CD transpose xi, or lambda CDTI. And if we take a look at the size of lambda, then it is 180. And indeed, what is the size of the beta vector? Well, we have seen that before in the initialization. This is size x. So it is given the size of beta vector, the output lambda here, is given by the number of arrivals, C, times the number of days plus holidays, capital G, times the number of elementary time windows in the period considered by the modeler, times the number of regressors, which is n-Belan types plus 1. Indeed, we have the betas are indexed by CDT, beta C, GT, and every beta CDT as dimension n-Belan types plus 1. And we see that this CDT times n-Belan type plus 1 is indeed 180, which is the size of lambda of the output. And as before, the vector obj contains the approximate optimal values of the optimization problem that we are solving along iterations. I can show you that indeed the algorithm converged since we get stabilization of the approximate optimal value after some iterations. So this concludes the presentation of LASPATED function, calibrate model with covariates.